What if I told you the universe is stranger than we ever imagined? What if the very fabric of space, the galaxies scattered across billions of light years, were hiding secrets that could completely change how we see everything around us? For decades, astronomers have peered into the cosmos using powerful telescopes to glimpse the faint glow of distant stars and galaxies. Yet, even with the most advanced instruments, there was always a limit, a boundary to how far back in time we could see, a horizon beyond which the universe remained a mystery, until now. Enter the James Webb Space Telescope. Launched in December 2021, this technological marvel is the largest and most powerful space telescope ever built. With a mirror nearly 7 meters wide and instruments sensitive to infrared light, it can peer farther into the cosmos than any telescope before it. Its mission is bold: to look back in time to the first few 100 million years after the Big Bang and to uncover the birth and evolution of the earliest galaxies. Simply put, JWST doesn't just take pictures, it captures history, frozen in light that has traveled for more than 13 billion years to reach us, and the discoveries it has begun to reveal are nothing short of astonishing. Early galaxies, larger and brighter than scientists predicted, appear in places where we thought only tiny chaotic formations could exist. Cosmic dust clouds that have long hidden the processes of star formation are now laid bare. Chemical elements like oxygen, carbon, and dust, once thought to appear slowly over time, are revealed in the earliest epochs of the universe, and that's just scratching the surface. Scientists are now revisiting their models of how galaxies form and evolve, how stars are born, and how the universe became enriched with the elements that eventually made planets and life possible. Headlines may call it shocking or unbelievable, but the truth is, this is exactly what science is meant to do: push the boundaries of what we know, challenge our assumptions, and inspire us to ask even bigger questions. What James Webb is showing us is more than just distant galaxies. It is a glimpse into the universe's deepest history, a window into cosmic events that shaped everything we see today. And what it's showing us could change how we think about the universe forever. What JWST actually does: the James Webb Space Telescope isn't just another telescope, it's humanity's most powerful eye on the cosmos. Unlike telescopes built to see only visible colors like those our eyes can perceive, Webb was designed to detect infrared light, which is light that has been stretched to longer wavelengths as it travels through space. This is crucial because when light from the earliest galaxies travels for billions of years, the expansion of the universe stretches that light into the infrared part of the spectrum. By observing in infrared, Webb can capture light from objects so distant that their light has been shifted far beyond what visible light telescopes can detect. Infrared light also has another powerful advantage: it can pass through dense clouds of cosmic dust that normally block visible light. That means Webb can peer into stellar nurseries and dusty regions where stars and planets are forming, places where traditional telescopes see little more than darkness. To make this possible, Webb carries a tennis court-sized sun shield that keeps its instruments extremely cold and prevents the telescope's own heat from interfering with the delicate infrared light it captures. Webb's main mirror is another part of what makes it extraordinary. At 6.5 meters in diameter, it's nearly 3 times wider than the Hubble Space Telescope's mirror. That larger size gives Webb a much bigger surface to collect faint light, which is essential for detecting galaxies that formed in the universe's first few 100 million years. The mirror is made of 18 hexagonal segments coated in gold to enhance infrared reflectivity, allowing it to gather more light from extremely faint and distant sources. But Webb doesn't just take pictures, it also analyzes the light it receives in an incredibly detailed way. Its instruments include cameras and spectrometers that break light into its component wavelengths, revealing chemical fingerprints. This means Webb can not only see distant galaxies, but also detect the chemical composition of exoplanet atmospheres, identifying molecules such as water vapor, carbon dioxide, and methane. By examining how starlight changes as a planet passes in front of its star, scientists can infer the presence of these molecules and learn about conditions on distant worlds. All of these capabilities make JWST a revolutionary scientific tool. It can see galaxies from more than 13 billion years ago, offering a view of the universe when it was still in its infancy. It can peer through dusty regions to watch stars being born, and it can decode the atmospheres of planets light years away. This isn't a byproduct of accident. This deep, detailed detailed and infrared view of the universe is exactly what Webb was built to do, to push the boundaries of what we can observe, understand, and imagine. Early galaxies, JWST discovered. When astronomers talk about looking back in time, they mean seeing light that has traveled across almost the entire history of the universe to reach us. The James Webb Space Telescope has done just that, capturing light from galaxies that existed only 300 to 500 million years after the Big Bang, a period known as the Epoch of Cosmic Dawn, when the first galaxies were beginning to form from primordial gas. Before Webb, our deepest views into the infant universe came from the Hubble Space Telescope, which could see galaxies that formed around 800 million years after the Big Bang at best, but Webb's infrared sensitivity lets it push that limit far earlier. Among the most remarkable discoveries are the galaxies named J-Days GS-Z14-0 and J-Days GS-Z14-1, which appear as they were roughly 300 million years after the universe began, just a tiny fraction of its 13.8 billion year age. These galaxies are not just ancient, they are surprisingly large and bright for their age, with JD's GS-Z14-0 spanning about 1,600 light-years across. That amount of size and luminosity so early in cosmic history goes beyond what many models predicted, leading researchers to ask how such galaxies could assemble so quickly. This challenge comes down to a fundamental question in cosmology: how did the first cosmic structures grow so fast? Traditional theories suggested that early galaxies should be small, dim, and irregular, formed slowly as gas clumped together under gravity and gradually built up into larger systems. Instead, Webb is finding galaxies that are not only visible but luminous, structured, and forming stars at astonishing rates. The brightness of these early systems suggests that stars were being born rapidly, producing ultraviolet and infrared emission that Webb's instruments can detect even after being stretched by cosmic expansion. Even more surprising is that some observations hint at galaxies forming stars in bursts, in which star formation happens in intense episodes rather than a slow, steady process. These bursts can make galaxies appear exceptionally bright, helping explain why Webb detects so many early systems in a relatively small patch of sky. This finding suggests that early galaxy growth could have been far more dynamic and varied than expected, with some forming stars quickly and then fading while others continued to shine. But the story doesn't stop at size and brightness. Other Webb observations are uncovering galaxies that show signs of complex features like ionized hydrogen bubbles, indicating that early galaxies were powerful enough to ionize the surrounding cosmic gas and help end the universe's so-called dark ages. A galaxy detected at around 330 million years after the Big Bang reveals such a massive ionized region, suggesting vigorous star formation and intense radiation that reshaped its environment. So the discoveries Webb is making are not random anomalies, they're direct physical clues about how galaxies assembled in the very early universe. Each new detection pushes scientists to refine their theories about cosmic dawn, not because the universe is defying physics, but because the universe was clearly busier, brighter, and faster at building its first galaxies than we expected. No Big Bang violation. When the James Webb Space Telescope started revealing galaxies that seemed to exist only a few 100 million years after the Big Bang, some sensational headlines screamed that the Big Bang theory was broken or that the universe must be older than we thought. But that's simply not the case. The reason astronomers can talk about the age and expansion of the universe is because of a property of light called redshift. As space expands, light traveling through it is stretched to longer, redder wavelengths. The more distant a galaxy is, the more its light is redshifted, and that redshift tells scientists how far away in space and time that galaxy is. This relationship between redshift and cosmic age has been tested and confirmed in multiple independent ways, including the cosmic microwave background and supernova measurements, and remains a cornerstone of modern cosmology. The existence of bright early galaxies doesn't rewrite the Big Bang, it refines our understanding of how galaxies formed after it. The standard cosmological model, called lambda CDM, describes the overall expansion and history of the universe extremely well. It does not make precise predictions about the exact size or brightness of every early galaxy, because those depend heavily on complex astrophysical processes like star formation, black hole activity, and gas dynamics. JWST is revealing that some early galaxies are forming stars in rapid bursts, or may contain active black holes that make them brighter than expected. These are surprising discoveries, but they don't contradict the age of the universe or the redshift distance estimates that support the Big Bang framework. It's also important to understand the difference between unexpected and impossible. Science often progresses by encountering phenomena that don't fit our initial models. When Hubble first launched, astronomers didn't expect the accelerating expansion of the universe, yet that discovery didn't overthrow relativity, it extended it. The same goes for JWST's deep observations. They challenge galaxy formation models, not the underlying physics of the universe's expansion. Researchers are actively updating simulations and theories to include effects like bursty star formation, more efficient gas cooling, and early black hole growth, which can produce the bright, early galaxies Webb sees without rewriting the cosmos's age or rejecting redshift as a valid measure of distance. So, sorry to spoil the clickbait, the universe isn't older than your last birthday, and JWST hasn't disproven the Big Bang. What it has done is show us that the early universe was a more dynamic and complex place than we realized, giving scientists rich new data to improve our cosmic story. Chemical elements in early galaxies. When the universe first began after the Big Bang, it was made almost entirely of the simplest elements: hydrogen, helium, and tiny traces of lithium. Heavy elements like carbon and oxygen didn't exist yet because they are forged inside stars over time. But thanks to the James Webb Space Telescope's unprecedented sensitivity in infrared light, astronomers are now detecting oxygen, carbon, and even complex carbon-rich dust in galaxies that existed when the universe was still very young, some less than 500 to 700 million years old. These discoveries suggest that the first generations of stars lived fast, burned brightly, and produced heavy elements far earlier than many models predicted. In some of the earliest galaxies Webb has observed, scientists have measured significant oxygen abundance, a surprising result because oxygen is created in the cores of massive stars and dispersed when those stars explode as supernovae. Webb's instruments, especially its spectrometers, can break the light from these distant galaxies into detailed spectra, revealing the unique fingerprints of elements like oxygen. Recent studies measuring oxygen in galaxies from around 500 to 700 million years after the Big Bang show that this element became abundant quickly, indicating that multiple generations of stars must have formed, lived, and died in rapid succession. Carbon, too, is turning up in places where scientists once expected only the simplest elements. Observations of galaxies, seen as they were around 350 to 400 million years after the Big Bang, reveal carbon signatures at levels that challenge previous assumptions about when heavy elements should appear. This carbon is not just in individual atoms, it is part of carbonaceous dust grains, the building blocks of complex molecules and eventually planets. The surprising speed at which such dust forms suggests that stars in the early universe were evolving and enriching their environments much faster than expected. To put this in human terms, imagine you thought it would take centuries to bake a complex cake, only to find out it was done in weeks instead. That's similar to what Webb is showing us about cosmic chemistry. Stars produced heavy elements and dust in far shorter time spans than we once believed possible. These early chemical enrichments don't violate physics. They reshape our understanding of how the first stellar generations worked and how quickly the universe became chemically complex enough to eventually support planets and, perhaps much later, life. Exoplanet atmospheres. When astronomers first began looking at the atmospheres of planets beyond our solar system, the view was dim and blurry, literally just hints of what might be there. The James Webb Space Telescope changed all of that. By watching how starlight filters through a planet's atmosphere as it passes in front of its star, Webb's instruments can break that light into a spectrum and identify the chemical fingerprints of gases like water vapor, carbon dioxide, and methane. This technique, called transmission spectroscopy, is what allows scientists to decode exoplanet atmospheres with a level of detail previously impossible. One of the early breakthroughs came from the exoplanet WASP-80b, where Webb detected both water vapor and methane in its atmosphere. Methane had been notoriously difficult to detect with earlier telescopes, so seeing its spectral signature clearly with Webb was a milestone for exoplanet science. These molecules, familiar to us on worlds like Jupiter and Saturn, tell us not only what these alien atmospheres are made of, but also how chemical processes operate under wildly different conditions from those in our own solar system. Webb has also revealed more exotic atmospheric chemistry, In the case of the Neptune-like planet WASP 107b, scientists found water vapor, sulfur dioxide, and even silicate sand clouds, a bizarre weather system unlike anything on Earth. The presence of sulfur dioxide and cloud particles high in the atmosphere defied earlier expectations and gave researchers a peek into complex photochemical processes at work. These discoveries underscore how Webb's infrared sensitivity opens a window into details that Hubble and other telescopes simply couldn't reach. Another fascinating case is K2-18b, a world that orbits within its star's habitable zone. Webb observations have detected methane and carbon dioxide in its atmosphere, and tentative signs of dimethyl sulfide, a molecule on Earth often associated with biological activity, though that detection is still being investigated and isn't confirmed as a sign of life yet. Webb isn't saying we've found aliens, but it is telling us that some exoplanets have atmospheres rich in complex, life-relevant chemistry worth studying further. All of these discoveries show that JWST doesn't just spot distant planets, it measures their atmospheric chemistry with precision, helping scientists ask deeper questions. What makes an atmosphere stable? Could some conditions support liquid water? And yes, could one of these planets ever host life as we know it? While no direct evidence of life exists yet, every spectrum Webb captures brings us closer to understanding these alien worlds. Star formation hidden by dust. When we look at star-forming regions with ordinary telescopes like Hubble, what we often see are glowing outer walls of gas clouds where the light is visible. But the really interesting action, the places where stars are actually being born, is often shrouded in thick cosmic dust that blocks visible light. Hubble's sharp vision is limited by the fact that dust absorbs and scatters optical light. It's like trying to see into a foggy forest with just a flashlight. Infrared light, which Webb was specifically built to detect, passes through that dust, revealing structures and newborn stars that were previously invisible, much like switching on a bare bulb lantern in a dark room and discovering a hidden city of stellar nurseries. One of the most dramatic early examples of this came from Webb's infrared view of the Carina Nebula, a vast star-forming region about 7,600 light-years away. In optical images, Carina's dense walls of gas and dust look mysterious and opaque, but Webb's infrared instruments unveiled a spectacular landscape of deeply embedded young stars and protostellar jets, outflows of gas driven by infant stars pulling material from their surrounding clouds. These jets and outflows are signposts of intense star birth, previously hidden from view, that help astronomers understand how stars accrete matter and evolve in their earliest phases. Astronomers call one of these regions the cosmic cliffs, the edge of the nebula's massive gas cavity, because it resembles towering pillars and rugged terrain carved by powerful radiation and stellar winds. Webb's infrared image of the cosmic cliffs shows bright young stars emerging from deep within dusty filaments, features that were either faint or completely invisible in Hubble's optical pictures. By monitoring these structures, researchers are now counting and categorizing stars down to smaller masses and earlier stages of formation than ever before. The reason Webb can do this is simple. That means Webb can peer into the heart of stellar nurseries where gas and dust collapse under gravity to form new stars, giving us a direct view of processes that were once accessible only through indirect clues. These observations not only confirm theories that stars form deeply hidden within dusty cocoons, they also challenge astronomers to refine models of star birth by showing how jets, outflows, and embedded clusters influence their surroundings. JWST's infrared vision is allowing scientists to study the full life cycle of stars in their native environments, turning what were once opaque, mysterious regions into rich, dynamic landscapes of stellar creation. What JWST did not find. Despite the wild and sometimes dramatic headlines you might see online, the James Webb Space Telescope has not discovered aliens, detected a hidden edge of the universe, or proven that the universe is a simulation. Webb was built to observe light from extremely distant objects and reveal their properties, not to spot alien civilizations or secret spacecraft. Claims that the telescope has identified an alien ship or similar small object are simply unfounded. Technically, Webb doesn't have the resolution to detect something as small or as close as that across interstellar distances. Another persistent myth is that Webb's findings somehow disprove the Big Bang theory or overturn cosmology itself. While it's true that some early galaxies appear larger or more evolved than models initially predicted, these observations don't negate the vast body of evidence supporting the expanding universe and cosmic history. Scientists themselves have explained that rather than disproving the Big Bang, Webb's data refines our understanding of how galaxies formed and evolved in the early universe. Similarly, there is no credible evidence from Webb that the universe has a physical edge or that our reality is a simulation. Such claims fall into the realm of speculation rather than science. Webb's data reveals more detail and complexity in the distant universe, but it does not violate fundamental physics or the well-tested frameworks of general relativity and cosmology. The surprising discoveries are exciting precisely because they expand our understanding, not because they break established laws. So if you've seen sensational titles promising cosmic upheaval, take them with a grain of salt. Webb isn't rewriting the rules of physics, it's giving us far richer and more detailed information about the universe's earliest epochs, which scientists will use to improve models and deepen our cosmic knowledge. And yes, sorry, no intergalactic traffic jams yet. Implications for astronomy and future discoveries. The James Webb Space Telescope has done more than just take stunning images, it has reshaped key parts of modern astronomy. Because Webb can see farther and more clearly into the early universe than any telescope before it, scientists are now reconsidering how fast galaxies formed, how stars were born, and how the cosmos evolved in its first billion years. Observations of unexpectedly large, bright, and well-structured galaxies from just a few 100 million years after the Big Bang have challenged existing galaxy formation models, suggesting that the early universe may have been more dynamic and efficient at assembling structure than previously thought. These findings are prompting astronomers to refine theories of cosmic evolution, not discard them. For example, Webb's data on early star formation rates, chemical enrichment, and galaxy structure are being used to update simulations that track how small fluctuations in the young universe grew into the vast cosmic web we see today. This includes improving models for how stars formed more rapidly and produced heavy elements earlier than expected, information that feeds directly into our broader understanding of the chemical and structural evolution of galaxies. But Webb's impact isn't limited to just galaxy formation. Its sophisticated instruments will continue to observe exoplanets, protoplanetary disks, and the atmospheres of distant worlds throughout its mission, helping scientists better understand planet formation and the diversity of planetary systems. By measuring the chemical fingerprints of molecules like water, carbon dioxide, and methane, Webb is paving the way for studies that could one day identify planets with conditions suitable for life, though we haven't found life yet. Webb is giving us the tools to explore that question in detail. Looking ahead, future observations with Webb will probe even deeper into the cosmic dawn, helping answer questions about the earliest stars, the processes that ended the universe's dark ages, and how Ryanization unfolded. Webb's data, combined with other observatories like ALMA, Euclid, and future telescopes, will create an integrated picture of how the universe grew from a nearly uniform sea of gas into the rich, structured cosmos we inhabit today. In the end, James Webb has not answered all our questions, it has revealed how many questions we didn't even know to ask. The universe still has secrets, and JWST is just getting started. Each new image and spectrum brings us closer to understanding our cosmic origins, reminding us that we are explorers at heart, driven by curiosity that knows no bounds. As we've seen, the James Webb Space Telescope is doing more than just taking breathtaking images of the cosmos. It's transforming our understanding of the universe itself, from revealing galaxies that formed just a few 100 million years after the Big Bang, to detecting oxygen, carbon, and dust in those early galaxies. Webb is showing us a universe that is far more dynamic and complex than we imagined. It has measured the atmospheres of distant exoplanets with unprecedented precision, detecting water vapor, carbon dioxide, and methane. And it has unveiled star formation hidden behind thick clouds of cosmic dust, giving us a look into stellar nurseries previously invisible to Hubble and other telescopes. These discoveries are not just scientific milestones, they are a reminder of the boundless curiosity and creativity that drives human exploration. The universe is a place of endless wonder, and Webb is giving us the tools to uncover its secrets like never before. Now we want to hear from you. Which of these discoveries surprised you the most? The ancient galaxies, the chemical fingerprints of early stars, the hidden stellar nurseries, or the atmospheres of distant exoplanets? Share your thoughts in the comments below. If you enjoyed this journey through the cosmos, don't forget to like, share, and subscribe to stay updated on all the latest JWST discoveries. The universe still has mysteries to reveal, and with every new observation, we're one step closer to understanding our place among the stars.